If you're in the lab, some of you have already started doing lenses in lab. We'll deal with two types of lenses. In lab, you just deal with this first one. This first lens is called a convex lens. This is also called a converging lens. You got to be careful because the lenses and the mirrors are different. Like they have different names. Remember, this first word describes the geometry of the object. So this convex lens, it looks like a convex mirror, sort of, right? Convex mirror is shaped like this, but it doesn't act like a convex mirror. It acts like a concave mirror because it's a converging device. So it's called convex because of the shape of it, but it's called converging because of what it does to light. Right? And if you remember, the concave mirror was a converging device as well. So this thing acts more like a concave mirror. If you remember that, that'll sort of help you to keep these sorted out in your mind. So remember, convex refers to the geometry. And so it looks like a convex mirror. But it doesn't act like a convex mirror because this is a converging lens, and this describes what it does to the light. Right, it causes the light rays to converge to a point. This is like when you use your magnifying glass to set fire to your hand or whatever, right? Have y'all gone home and tried to do this? How hot that little spot gets? It's really hot. Okay, so what it does to light, it's a converging lens. So the convex lens, it acts like a concave mirror. And we'll see that when we do our ray diagrams, that the ray diagrams for the convex lens are a lot like what we saw for the concave mirror. Now, this other lens, gosh, what do you think this lens is called? I'm sorry, what? Concave, yeah. So this is a concave lens. All right, but this is a diverging lens. All right, so it looks like a concave mirror. It looks like it, but it acts like a convex mirror. If you know your mirrors well, that will help you with the lenses, but you just need to make sure that you understand that they're different, that they've switched names now. Just to confuse you, I guess. I don't know why. Well, because convex refers to geometry, converging refers to what it does to the light. Okay, we have different types of lenses too. They're fairly straightforward. Like, for example, they're like compound words. So a plano-convex is planar on one side, and convex in geometry on the other side. It's like it's poking out its belly on the other side. Concave, convex. This side is concave. The other side is convex. Meniscus is very similar, but it's slightly a different shape. Don't worry about the meniscus. We're not going to sweat that right now. And then the plano-concave is planar on this side, is flat, and concave on this side. The focal length we define in the same way. So for these lenses, just make sure that you can identify them. Just know what those words convex and concave mean. And you might have some pictures of these various lenses, and you just have to know what they're called. We're not going to use them in any kind of optical system. All right, the focal length of a lens is defined same as we did for the mirrors. It is the half the radius of the sphere. Half the radius of the sphere from which the lens was cut. I say cut because you don't actually start with a sphere of glass, of course, and cut out a lens. But you can really think of it in that way, that actually you have two spheres that come together, and where they intersect is where our lens is. So unlike with the mirrors, the lenses will have two curved surfaces. With the mirrors, we just have one curved surface, right? But with the lenses, we're going to have two curved surfaces. This is a convex mirror lens. The convex lens is the intersection of these two spheres, and this is our radius of the sphere. Remember, this is called the center of curvature. And the focal length is just half that distance. So our focal length is equal to c divided by 2. Notice that each side of the lens has a different focal point. However, in this class, we'll always deal with lenses that have the same focal point on both sides. That's not uncommon, actually. Like in the lab, you probably have a lens with the same focal point on both sides. It's only in very special cases where you have different focal points on different sides. So we'll just deal with it where we have the same focal point on both sides. So we will assume our lenses have the same focal point. On both sides. That the curvature of both sides is the same. All right. By the way, with a concave lens, you can think of it in this way. You can think of having these two spheres like this, and then where the spheres come together is the concave lens. All right, we have these two spherical surfaces that are described by a sphere, and they have a certain radius, and that gives us a focal point. Okay, you with me on that? Two sides of our lenses. Each of them have a radius of curvature, and each of them have a focal point. Further, you remember with the mirrors, we could define our center of our focal point by our center of curvature, but we also define it by where light rays converged. And we're going to do the same thing with lenses. So, for example, with a converging lens like this, if we have parallel light rays that come in, they're going to focus at the focal point. Where those two rays cross is where our focal point is. For a diverging lens, so this will, by the way, will be one of our rules. Remember, for our mirrors, we have a similar rule. If I have a parallel ray, it focuses at the focal point. All right. And I also just want to remind you, this is called a convex lens. Well, like I said, it acts a lot like a concave mirror. This is a concave mirror. And parallel light rays here also focused at the focal point. Right, these, they might look a little different, but they really act a lot the same. Also, I'm just going to go ahead and point this out. I'll write this down later. But remember with the concave mirror, if I formed an image on this side, what type of image was that? A real or virtual image if it was on this side of the mirror? Right, it's like this is the real space, and this is the virtual space, and everything that's over here has a positive value, and everything that's over here has a negative value. Well, you'll see that with lenses, it's different. Over here is the virtual space, and over here is the real space. So when I form an image on this side of the lens that is opposite the object, then I'm going to have a real image. When I form an image on this side of the lens, that's going to be a virtual image. Don't sweat that right now. I'll write that down later, but I just want to point it out to you if you're following along with mirrors. So convex lens and concave mirror work a lot the same. For a diverging lens, I have light rays that come in. Now, a diverging lens will cause the light rays to diverge from one another like this. But they cause them to diverge in such a way that if you were to trace them back, they would go through the focal point. So that's how we describe what is the focal point. Half the center of curvature, or the place where parallel light rays focus, either in real or in virtual space. And again, for the lenses, this is going to be our virtual space. If you want to think of it in that way, where everything has a negative value, and the other side will be our real space, where everything has a positive value. All right. With both of them, I'm going to exaggerate the concave lens, make it more curved. Imagine that if I have light rays that come in, so I have a light ray that comes in, you can imagine that it has wave fronts like this. As these wave fronts move in, it's going to hit this curved surface first, just because of the geometry of it. And since this side, the light will enter the medium here, but down here it hasn't entered the medium yet. That means it's going to be traveling faster on the bottom side of the wavefront, which is going to cause it to turn up, just like we saw in the previous chapter for the law of refraction. So this wavefront right here, it slows down right here. It's still traveling fast here. That's going to cause it to bend in that direction. And then similarly here, it's going to speed up right there. It's still traveling slow there. It's going to cause it to bend more. So we're really just dealing with refraction now, just like we had in chapter 6 or so. You can sort of reason out with yourself just by drawing the pictures which way the light is going to bend for the converging or the diverging lens. This is the diverging, but you can do a similar thing for the converging. Okay? All right. Let's look at magnification. A lot of our stuff is still going to hold true. Magnification is still minus Q over P. Magnification is also still going to be HI over HO, just like what we had for mirrors. We'll have the same sign conventions. So if we have a magnification greater than 1, it's a bigger image. Less than 1, it's a smaller image. If it's equal to 1, it's the same size. If my magnification is positive, it's upright. If it's negative, it's inverted. Our lens equation is the same. 1 over F equals 1 over P plus 1 over Q. So all that is the same as we had for mirrors. However, there are a few important differences. If the object is in front of the lens, so let's say this is our lens. Let's say that this is the front. I'll typically draw front on the left and back on the right. If our object is in front of the lens, that's going to be plus P. Listen, our object is always going to be on the front of the lens, except when we get to 2 lens systems. And then it's usually going to be in front of the lens, but sometimes we'll see that it's not. So don't worry about having a negative P right now. We'll see that when we get to a 2 lens system. So just assume for now that your P is always going to be positive. And then later when we do 2 lens systems, you'll see that that's not necessarily true. So I'm just going to sort of cross this out for now, and we'll come back to it. For my image distance, if my image is in front of the lens, wait a minute, hold on. Yeah, if my image is in front of the lens, that's a negative Q value. If my image is in the back of the lens, it's going to be inverted actually, then that's going to be a positive Q value. Notice, by the way, that I drew my image inverted, because remember, since M is equal to negative Q over P, if Q is positive, the magnification is negative. All right? So if Q is positive, that means I have an inverted image. That means that all real images for a single lens system are going to be inverted. All virtual images are going to be upright. We had that for mirrors too, but all real images are what? Inverted. All virtual images are upright. Yeah. You seem really excited about these lenses. Is it just me, or is it like you really are excited about them? You really are excited? That's awesome. Yeah, great. Okay, now the focal length for convex lenses, gosh, what do you think it is? The convex, remember, looks like this. Concave looks like this. The focal length for concave lenses is positive or negative, what we know already. Let's do it as a clicker question. So, is it positive or negative? The focal length for convex lenses, is it positive or is it negative? What we know already. All right, we'll stop at, say, 32. You might not a priori know this, but I think you can reason it out. Okay, good. It is positive. Remember, because the convex lens, it's like a concave mirror, so it has a positive focal length. Remember, just like a concave mirror. The focal length for the concave lens then is negative, and that's just like the convex mirror, like the security mirror. So remember this, that's a little bit different for lenses because the names have now switched positions. All right, let's try another clicker question right here. All right, this one's pretty easy. It's not easy, but concave lens, focal length of 10 centimeters. Object is located at 10. Where is the image? All right, we'll stop at 110. Or go on to 115. Okay, great. Listen, a lot of you, some of you put B. B is a good wrong answer. I'll show you what you did wrong. In fact, if you put B, you might have put it almost immediately because you thought, well, gosh, if I have an object at the focal point, then it shouldn't produce any image at all, right? And so that's why you put B, or it might have been that you came up with an error in your calculator. But the one thing that you are missing is that concave lenses have a negative focal length. So my focal point on a concave lens is actually negative 10. So if I do this, I get 1 over F equals 1 over P plus 1 over Q. 1 over F, that's 1 over negative 10, equals 1 over 10, that's my p-value, plus 1 over Q. And so I get negative 2 over 10 equals 1 over Q. So Q is equal to negative 5. Make sure you can work with that equation and do the various inversions that you need to do. So it is 5 centimeters. When it's negative, that means that the image is over here. So this is the object, this is the image. It's 5 centimeters to the left of the lens. I know it's to the left because the negative tells me that the image is the same side as the object. Because that's where virtual images are for lenses. Unlike for mirrors, virtual images are on this side of the lens. Real images are on that side of the lens. If you ever forget, think about the projector. It makes a real image, right? This is a real image. It's projected onto a screen. The lens is up there. The source of light is opposite side of the lens, and the image is over here. Or you can think about your eye. We'll look at the eye and how it works a little bit later. You have light coming into your eye, so the object is outside of your eye. You have the lens, and then you have the real image projected onto your retina. Okay? So remember that your image is on the same side as the object. Let's try this next one. Do your best on this. I'll help you. It's a little wordy. Have y'all done this before? Have y'all talked about this in anatomy, how the focal length of the lens changes? No? Like y'all are just all really smart? Do you just know this? Okay, good. I'll stop at 135. 135. That's awesome. C is the right answer. Usually see this one through as well. So the eye looks like this, right? It's basically a sphere. It has a lens. Actually, the lens is made up of your cornea and the lens inside, which is this sort of fluid-filled thing. The lens actually does most of the refraction. The cornea, take that back. The cornea does most of the refraction as it goes from air to the corneal surface, and then your lens does sort of fine tuning of the refraction. So if you have an object that's really far away, my light rays will come in and they'll focus back here. This is my retina. You know, the light goes to the back of your retina, it stimulates all those rods and cones, and then it transfers that into an electrical signal, sends it to your brain. And then your brain, you know, does what it does with that signal. Now, in this case, the focal point is right here, right? My focal point is there. Now, if I'm looking at something that's closer, my focal point is going to decrease, as you all, or most of you said. Oh, shoot, sorry. And when that happens, the lens actually gets sort of fatter in the middle. I overestimated there. We'll see this with the we'll see this with ray diagrams. Yeah, don't worry about this diagram, actually. We'll see it with ray diagrams. But when you focus on something that's closer, your focal point moves in. It's like your eye sort of squeezes down on that lens, that fluid-filled lens, and makes it fatter in the middle, which increases or decreases your focal length. Okay? We're actually not going to spend that much time on the eye, but we will come back to this, and we'll see, talk about the eye a little bit more. Alrighty. Let's see. So I think there's another one. This weekend, my wife and I, we're planning to go. They're putting on this like theatrical production, and it's like nothing but puns. It's all puns. Isn't that crazy? It's a play on words. See, that's funny because not only was it like it's a pun in itself, right? The joke is a pun. Okay. A person uses a convex lens that has a focal length of 10 centimeters to inspect a gem. Forms a virtual image 20 centimeters away. What is the magnitude of the magnification? All right, we'll do about 10 or, yeah.
So are contact lenses concave lenses or convex lenses?
They're concave convex. But I think actually, I don't know, I think that they might just change the index of refraction of your eye a little bit. But they are convex on one side and concave on the other. I don't know much how they work. You shouldn't wear contact lenses. They're very bad for your eyes. I've been telling my wife this for years. It's like wrapping your eyeball in saran wrap. She's been telling us for years. And then the eye doctor finally told her like her eyes were really dry. She's like, why didn't you stop wearing contact lenses? So now she wears glasses. I think she looks better in glasses. Don't you agree? Okay. I'm sorry, I'm not an eye doctor, so I know like 3/4 of you wear contact lenses, and that's okay. But okay, I'm gonna stop at 2:45. Okay, not as good here. So, a couple things we need to recognize. Our focal length is 10. It is a convex lens, so that means our focal length is equal to positive 10. If it were concave, it would be negative 10. It does form a virtual image, so that's our Q value. Since it's virtual, it should be negative 20 centimeters. Some of you might have made that mistake. F is equal to positive 10. I do 1 over F, that's 1 over 10. Equals 1 over negative 20 plus 1 over P. And then I need to solve that for P, because really I'm trying to get to the magnification, which is negative Q over P. Let's see, so this is 1 over 10 plus 1 over 20 equals 1 over P. That's 3 over 20. So P is equal to 20/3, or what's that, 6.67 or whatever. And then my magnification is negative Q divided by P. That's negative 20 divided by 20/3. These cancel, the 3 flips up, and it becomes positive 3. So A is the right answer. I think if you put B, I think that your problem was here. Is that correct? If you put B? Okay, I forget what gives. I'm pretty sure B is where if you have your image distance positive. It should be negative though. So in these problems, as with the mirrors, make sure that you read the problems and think about different things like what type of lens am I using, or what type of image do I have, all that kind of stuff. It'll be similar to the mirror problems, where there'll be things that are unstated that you need to intuit or that you need to investigate. All right, let's do some ray diagrams. It'll be similar to the last part with mirrors, where you'll probably have a ray diagram, just like we had on the last one, where I give you one, I ask which of these rays is correct or incorrect. But further, it will also help you to know just what type of images are formed by what types of lenses. Our ray diagrams are very similar too. We draw a ray parallel to the axis. The optical axis. It bends or refracts and travels through the focal point. We draw a ray through the focal point. It bends and travels through. It travels parallel to the axis. So these are rules 1 and 2 are basically just the reverse of one another. 3, we're going to draw a ray through the center of the lens. And it passes through the lens with no refraction. That means it doesn't bend. So like for example, if I have a convex or a concave, it doesn't matter. If I have a ray that goes through the center of the lens, it just keeps going straight. Okay? With the convex lens, we have 3 scenarios. With a concave, we just have 1. They look a lot like what they do for mirrors. So if you got the mirrors down last time, they're going to be very similar. uh, outside the focal point, this is just like concave mirror outside the focal point. Gosh, do y'all remember what kind of image a concave mirror formed outside of the focal point? Was it real or inverted? I mean, excuse me, real or virtual? It was a real image, upright or inverted. I said inverted. Bigger or smaller, it can be either, right? So here, I draw a ray. I'm going to draw one here, parallel to the axis, through the focal point. I can draw another one through the focal point, parallel to the axis, like that. And then a fourth one, or excuse me, a third one, I can draw through the center of the lens. And where they cross, if you do this carefully with a ruler, they'll all cross. And where they cross is where the image is. Since they cross below the axis, that means that it's inverted. Since the image is over here, it's a real image. So I have a real inverted image. And it can be bigger or smaller. Now, P is positive. Q is positive or negative? It's a positive value for Q. And my magnification, positive or negative? Negative, because it's inverted. All right? Q is positive because it's real. M is negative because it's inverted. Keeping it real. Isn't that what they say? Keeping it real? Is that what they say? Yeah. Listen, I loaded Snapchat onto my iPod last night. What is that anyway? What do you do with it? Do y'all know? Is it just to send pictures to people? That's all you do with it? Huh? Oh, you can talk to people?
Well, like in pictures. Like sex. You can do like videos on it now too. That like you can watch like discovery or like a mystery or like there's like Fox News and stuff like little stories every day that they can.
It's just little image. They send you images.
You go like Cooking and you just like read through their story.
Oh, okay.
Yeah.
Oh, it's like a magazine. Okay, I'm gonna delete it this afternoon because it seemed pretty useless. All right. Okay, so if I'm at the focal point, parallel to the axis, through the focal point, I can't draw a ray through the focal point, so I have to go to the third rule, which is just through the center of curvature. Notice those rays are parallel, they're never going to cross, so there's no image. Here I have a positive P, and Q, if you calculate Q, comes out to be infinity. Right, 1 over F equals 1 over P plus 1 over Q. If P equals F, then I get 0 equal to 1 over Q. And so Q is equal to infinity. So infinity is where these rays cross, meaning to say that they never cross. And then the third one is the more difficult one because you're dealing with virtual rays. I draw a ray parallel to the axis and through the focal point. All right, this next one is a little difficult because the question is when you draw it through the focal point, well gosh, which focal point do you draw it through? In this case, you're going to draw it through the focal point on this side. So it's like the ray comes up like that as if it's coming from the focal point. So this is through the focal point and then parallel to the axis. Through the focal point and then parallel to the axis. And then the third one is going to be just through the center of the lens, like that. Then if I trace all those back, I find out where the image is. It's there. It's there. And it's there. Oop, oh, sorry, that was the wrong color. Y'all get the idea. All right, so where those three rays cross is where my image is. These, by the way, are called virtual rays. We have those with mirrors too. Because they're in that virtual space. Remember, our virtual space is on this side of the lens, which is the same size as the object. Let's see, P is positive here. P will always be positive until we get to 2n systems, and then sometimes it'll be negative. Q is positive or negative? It's a negative value, and M is positive or negative? It's positive, and M here is always bigger than 1. This is like a magnifying glass. It will always have a magnification greater than 1. So I have a virtual upright. Virtual images are always upright. Bigger image. Virtual upright and bigger image. All right, let's do concave lenses. Actually, that wasn't that bad, was it? Let's do a concave lens. I go down. Oh. Okay. Now the concave lens, you just have one for this. Parallel to the axis and through the focal point. But gosh, like this thing doesn't make the light ray go down like this, right? We know that it diverges, so we're going to have it diverge such that if you traced it back, it would go through the focal point. So it's going to look like that. All right, and then we will go through the focal point and parallel to the axis, but not through the focal point on the left-hand side. It's going to be the focal point on the right-hand side. So the second rule looks like this. Oh gosh, this is tricky. I have a ray that comes up such that if you were to trace it forward, it would go through the focal point. All right, so this is through the focal point, and then it goes parallel to the axis, like that. That's not much better, sorry. Parallel to the axis. Right, the first one is parallel to the axis through the focal point, but it diverges and comes back through this focal point. The second one is through the focal point and then parallel to the axis. But it comes here, goes through the focal point, and then it goes parallel to the axis. And then the third one is just straight through the center of the lens. That one's the same. Like that. And then if you want to know where the image is, you trace these back. The blue one's already traced back. The magenta one's already traced back. It's right there. Listen, if you don't get this one, that's okay. This one's kind of tricky with all the different focal points and stuff. You're not going to see this ray diagram on the test, but you do need to know what type of image a concave lens forms. And this is real or virtual. It's a virtual image, upright or inverted. Upright. Virtual images are always upright. Bigger or smaller. It's always smaller. Yeah. So this is a virtual, upright, smaller image. Does this remind you of anything? What? Convex mirrors. This is just like the convex mirror. So these properties are just like the convex mirror. All right, let's do a few clicker questions. This is chapter 7 continued on. We've done some of these. Didn't we? We did some of these, right? We've done any of these? Okay, I'm sorry. We're going to skip ahead of these. Okay, here we go. Well, that's mirrors. Shoot. Are you sure we didn't do any of these? I'm sorry. We should have done these. What were we doing? Just messing around? I'm very, very sorry. Okay. Camera can be modeled as a simple converging lens, just a single converging lens. Focuses an image on the film. Camera is initially focused on a distant object. If you want to focus on something closer to the camera, what do you have to do? So initially, I have a lens. It's focused on a very distant object so that the light rays are coming in parallel. And I put my screen back here. Then I have something that is closer, and I put my screen where? Now my focal point of my lens is going to be here. Well, I want to draw that. First I focus on something that's really, really far away, so the light rays are parallel, and I put my screen here to get the image. What do I do when I look at something closer? What do I do with the film, right, the screen, the CCD or whatever? What do I do about that distance between the lens and the film? All right, I'm going to stop at 130. 130. We're sort of split on this. This is very similar to the eye problem. So I think you are split about half and half. Yeah. So here on the top one, my focal point is right here. My focal point is there and there. Now, unlike the eye, a lens and a camera can't change focal length. Now, you can change out the lenses and it'll change your focal length, but you can't change physically the focal length of the lens in a camera. So my focal length remains the same, like that. Now, where is my image going to be? Is it going to be inside the focal point or outside the focal point? Well, let's see. Let's draw our rays. So I have a ray that goes parallel to the axis and through the focal point, and then through the focal point and parallel to the axis. So now my image is back there. Before, my image was here, and now it's back here. So what do I have to do? Move the lens towards or away from the film? Well, I have to move it away. Right, so A is the right answer. 25 of you got it right. This is different from the eye, because with the eye you can actually change the focal length. Because with the eye, your distance to the film, this distance in the eye is fixed, right? It's just based on the diameter of your eyeball. But with a camera, since you can't change the focal length, you can move the lens towards or away from the film. All right? Your ray diagrams will help you to understand that better, I think, if you know how to draw your ray diagrams, kind of like this. All right. Oh shoot, this is not relevant anymore. Oh, is that it? All right, we'll have some more later. I might pull up some more. I'm sorry, we should have done those others before the last test. All right, let's look at combinations of lenses. These are easy, right? Combinations of lenses, you just have two lenses. You really just treat it as two lens problems. So you'll find that they're very straightforward. In a two-lens system, the image of the first lens becomes the object for the second lens. All right, so if I have two lenses like this, I have an object over here. I produce an image over here. So this is my first image. And it becomes the object for the second lens. So this now becomes the object. and my image is over here, this becomes my second image, my second and final image. All right? First object is right here, produces an image. This image becomes the object for this lens, and it produces another image. Let's do an example. They're pretty straightforward. I think you'll like them. All right, let's do this one. We'll do this one sample and then let y'all go. Is that okay? Of course it's okay. All right. Okay. So here, what is the position and magnification of the final image? All right. So we're going to work two problems. We have f1 equals 10, p1 equals 30, and I ask what is q1? This is p1, this is f1. I solve for q1, 1 over q equals 1 over f1 minus 1 over p1. 1 over q1, 1 over 10 minus 1 over 30. That's 3 over 30 minus 1 over 30. That's 2 over 30. So q1 equals 15 centimeters. That means that my image, oh, and then also my magnification, m1, is negative q1 over p1, which is going to be negative 15 over 30, or negative 1/2. So my first image is 15 centimeters to the right of the lens. It's inverted because that value is negative, and it's half the size of the original image. I'm going to draw it a little smaller. That's my first image. This distance is 15 centimeters. So now I'm ready to do the second one. This distance is 25 centimeters. I know that because the total distance between them is 40. It's just 40 minus 15 equals 25. And then it's just like another problem. So I now have f1 equals 20, f2, p2 equals 25 centimeters. That's this value. And I want to know what is q2. So I say q2 equals 1 over f2, that's 1 over 20, minus 1 over p2, that's 1 over 25. The inverse of that, that's 5 over 100 minus 4 over 100, that's 1 over 100. The inverse of that, so q2 is 100 centimeters. Don't worry, we're going to come back to this on Monday, so if this is not sitting well with you, then we'll come back to it and work through another. So that's q2. Not quite done yet. Just a second. M2 is negative q2 over p2. That's negative 100 over 25 equals negative 4. All right, so our magnification for this second lens is negative 4. That means my image is going to be 4 times this size, and it's going to be inverted. So is the final image going to be inverted or upright? It will be upright, and it's actually going to be 4 times this size, which was half this size. So the final image will be twice as big, upright, and 100 centimeters to the right of that lens. My total magnification is just the product, M1, M2, negative 1/2, negative 4, positive 2. We'll work through a couple more examples like that next time, and then we'll wrap up this chapter, okay? Have a great weekend. I'll see you on Monday.